Good afternoon once again. Today we are going to start another unit under electrodynamics. This is under electrodynamics. And we say that in electrodynamics we are going to look at only two major concepts according to our Diploma 3 syllabus, and this is electrostatics and magnetostatics. So these are the two major concepts that we want to look at under electrodynamics. And to start us off, we are going to look at our first unit, which is what? Electrostatics. Again, in electrostatics, we are going to focus on two major theorems. And these theorems, two major laws, and these laws are Coulomb's and Gauss laws. So we are going to focus our interest on two major laws, and which is Coulomb's and what? Gauss laws. So without wasting a lot of time, let us look at the first law, which is Coulomb's law. This is common from your electrical science that was taught in first year. You did a bit of Coulomb's law. So we are going to state it straight away as a statement. Our statement for Coulomb's law, and we can say the force between two very small charges separated, two very small charges separated by a distance which is very large compared to their size in vacuum, in bracket free space, in vacuum or free space, is proportional to the square, is proportional to the charge, is proportional to, each charge, and inversely proportional to the square of the distance between them. It is proportional to each charge and inversely proportional to the square of the distance between them. So we can have that mathematically and say that F is directly proportional, assume that there are two charges, Q1, Q2, and inversely proportional to the square of the distance between them. So we can say where I come and have them here, where let me just start with Q, where Q1 and Q2 are positive and negative charges are positive and negative charge quantities positive and negative charge quantities and R, that is the distance between the charges. Distance between the charges. So same equally I can come and express this. If we are to remove the proportionality symbol, then we can say that F can equally be represented as K, Q1, Q2 all over R squared, where K, again here, we can say, now let me call this as equation 1 first, where K is our constant of what? Of proportionality. Constant of proportionality. And it is the same as, and it is equal to 1 over 4 pi epsilon naught. And we also know that the value of epsilon naught is the same as 1 over 36 pi times 10 to power negative 9, which is the same as 8.854 times 10 to power negative 12 farad per meter, like so. So if we substitute our value of K in equation 1, then we are going to have so we are saying that substituting for K in equation 1. So substituting for K in equation 1, we are going to say that our force will be given by Q1, Q2 all over 4 pi epsilon naught R squared. We can equally call that as our equation number what? 2. So that is our representation of Coulomb's law. Now that we don't have any constant component, we don't have the constant of proportionality, it can also be represented as that. Now we can say again, if we continue further, just say consider 2-point charges. Consider 2-point charges Q1 and Q2. Q1 and Q2 situated at A and B, separated by a distance A and B, separated by a distance R meters as shown below. So if we have this as shown below, maybe we have our point charge, and we call that as Q1. Say that is R. Just a minute, the space is now proving to be so small. Let me draw it on this other end. So this is Q1, that is Q2. This be point A, we can even call it 1, and this be point, point B from our statement. Now that force on charge Q2 due to charge Q1 goes in that particular direction, and we'll represent that as F. We can say maybe AB, or we can say 1, 2. So let us say AB. Yeah. And that particular force now that goes in this other direction, that is a force on Q1 due to Q2, can also be labeled as F, FB, A bar. So now maybe we can say, according to Coulomb's, let me just write it here. According to Coulomb's law, I can say FAB bar can be represented as Q1, Q2 all over 4 pi epsilon naught r squared, which is the distance of separation. Now we have to include, you can see here I have a bar on top, meaning that it is a vector because it's moving in that direction from that to that. So this is the direction. So it is a vector quantity. So we'll have to represent that as A bar with a unit vector in the direction of A, B. So similarly, maybe call this as your equation number 3. So similarly, if we were to look at this particular force, again, we'll also say that it is represented as F bar BA is equals to Q1, Q2 all over 4 pi epsilon naught r that squared A bar unit vector B A. So that is how we represent that. Maybe call this as equation number 4. That be our equation number 4. Now let us assume that these positions of the two vectors were represented by a position vector, such that we have a different drawing. Maybe we can say this as we try to explain our point clear. We can see how we are still dealing with only Coulomb's law. So let us say this. If the location of point charges if the location of point charges Q1 and Q2 are represented by position vectors are represented by position vectors R1 bar and R2 bar respectively, as shown below. So we are saying that if they are represented by position vectors R1 and R2 bar as shown below, say we have an origin there, and have that is a straight line. So let me just try to do it well. So let me join the 2 points. like so. So say the origin is O or 0. So we have our position vector R1 bar and R2 bar. So this is charge Q1. Just pushed it aside slightly. Q1, and another charge here is Q2. Let me move upward in that particular direction. Say this is the other force. Let me have this as the other force. So we are saying that moving from 2 to 1, say this is point A again, that is point B. So this is the direction. The distance of separation here is R, and we can represent it also as in that direction, because we want to represent it as a vector. It is R, that vector is what? R, B, A. So this force is B, A, because it's from due to B to that particular direction. And this other force here, we want to have this particular direction. The movement is downwards. My point B, this is the direction. So I can also label this as R from A to B, which is what? A, B, bar. So because it is due to position vectors, say this is my position vector, it's a vector, it has direction. Similarly, that is also another vector with that kind of direction. So let us label these two forces. Let us see how we can represent. This is AB and this is BA. How we can represent AB and BA. So we can say F AB bar will be represented as, so we'll have Q1, Q2 over Q1, Q2 all over 4 pi epsilon naught, say R squared. Unit vector is A bar. So we'll have that notation R, A, B, like so. We have that as our vector. Similarly, now this be our equation number. We were at equation 3. 3. This should be equation number 4. Then again, we are saying that F BA bar will also be Q1, Q2 all over 4 pi epsilon naught R squared A bar R BA. Now, our point of interest is the two unit vectors. Yeah? So we can say where A R A B bar. Remember our unit vector when we started doing our vector analysis was, or it can be represented as R A B bar all over R A B bar magnitude. R A B bar the magnitude. Now if we come back to our drawing here, look at the direction. I'm moving from A to, for me to get RAB as a vector, it's from A to B. So that movement from A to B, and if you look at the position vector, it will be that to that. Yeah? So if I was to write it here, RAB bar is the same as the negative R1 bar and the positive of that. Yeah? Or rather, it is R2 bar minus R1 bar. Similarly, R BA bar is equals to, so now RBA, I'm moving from B, point B, which is this, going to point A. So it's the negative of R2 to the positive of R1. So we are saying that positive of R1 minus the negative of R2. and our r, if you are very keen, the distance r is common. The distance of separation is the same, so it doesn't matter the direction. So r, again, can also be given by the magnitude of RA B, which is also the same as the magnitude of RBA, like so. So that magnitude gives us the distance of separation. So now let us come back to our equation 4 and 5. Equation 4 and 5. So we've said here where A bar RAB is given by this. So if we rewrite that, we are saying that our RAB from what we have here will be R2 bar minus R1 bar. And our magnitude will be the magnitude of R2 bar minus R1 bar, like so. So we have that. This is our A bar, RAB. Similarly, borrowing from what we have there, we can say that our A bar, RBA, must be the same as R1, R2, all over R1 bar minus R2 bar. And their magnitude, we've stated that they are the same, so it doesn't matter. So our magnitude can still be represented here. We can say, yeah, the magnitudes are there already. There's no need of repeating that. Or rather, we can just write them. We can say R is the same as, that R alone is the same as the magnitude of R2 bar minus R1 bar, which is the same as the magnitude of R1 bar minus R2 bar. Now, if we substitute all this that we found here in our equation 4 and 5, then this is what is going to be generated. Yeah. If we make a substitution there in our equation 4 and 5, so we are going to have FBA bar being the same as Q1, Q2 all over 4 pi epsilon naught. Then we have R2, and R2 for the first situation will be R2 bar minus R1 bar. We have to square that. Then we multiply by its unit vector, which we've agreed it is R2 minus R1 all over R2 bar minus R1 bar, like so. So if we combine these together, this will give us what? Q1, Q2 all over 4 pi epsilon naught R2 bar minus R1 bar cubic. We have this at the center. Then into R2 bar minus R1, like so. At times, students tend to confuse the two. This is a vector, this is a magnitude, so we cannot cancel these terms here. They'll remain as they are. So this will be our this is FAB, not FBA, FAB. So this is FAB bar. So maybe we can say this be our equation number 6. So we then say similarly, FBA bar can be represented by Q1, Q2 all over 4 pi epsilon naught R1 bar, R2 bar cubic into R1 bar minus R2 bar cubic, and we have that as our equation number what? 7. So this is a representation of the same Coulomb's law using what? Position vectors. Using our position vectors. So say if we have more than a single, more than 2-point charges, if there are more than 2-point charges, then Coulomb's law can be done using superposition principle. So let us see how we can apply our superposition principle to handle Coulomb's law. So assume that I have point charges which are more than 2. So let me say this is a Qn. The distance is Rn, like so, up to some point there Q, test point Q. Then I also have probably this is R1. To some test point there, to charge Q1. Let me just do the drawing first. So we have that. The force due to Q1, let me call it as F1 bar. The force due to this, let me also call that force as Fn bar. So I can also generate other forces. Say this is R2. Some point there. Say maybe the third one. R3. Like so. So this is Q2. This be my Q3. So there's also a force there that generates that. Let me say this is F2. This force here, sorry, it's there. Let me have them at the top there. So this force, they need to be straight lines. That be F2. And maybe the third one, due to this, F3, and we have that as being what? Fn bar. So we have that, and we have that. Now, if we were to compute these forces, then we are going to apply our superposition theorem. And if we apply our superposition theorem, then we'll have F being given by individual forces, which is F1 plus F2 bar plus F3 bar, say plus, all the way up to plus what? Fn bar. So that is how we'll apply our superposition. And remember, our superposition principle or theorem. And remember, the distance of separation vary with all these charges. So we can say that F1, if we continue, we can say that F1 will be given by Q1, that Q, all over 4 pi epsilon naught R1 squared, say in the direction of A R1 bar, plus Q2 Q all over 4 pi epsilon naught R2 squared in the direction of A R2 bar, say plus Q3 Q over 4 pi epsilon naught R3 squared A R3 bar plus up to the end, and the last one say it is Q N Q all over 4 pi epsilon naught Rn, sorry, Rn squared A Rn bar. So that becomes our last whatever. So now if we look at this again, now we can factor out what is common in our expression here. And if we try to factor out the common terms from that, so we can say that our F bar, so our common term there is Q all over 4 pi epsilon naught. Then the rest are just summation from, say, K is equals to 1, from K is equals to 1 to infinity of QK all over QK all over RK squared, sorry, RK squared AR, ARK bar. So that is a summary of how we are supposed to sum all our terms there. And this can be our equation number 8 that summarizes that. So maybe in terms of position vectors, then we can also say that F bar can still be represented as F1, F2, F3, all the way up to Fn, and this will still be, it was Q1, Q all over 4 pi epsilon naught. Now we are assuming that our vector at test point is R minus R1 bar cubic into R bar R1 bar plus Q2 Q all over 4 pi epsilon naught R bar minus R2 bar cubic into R bar minus R2 bar, like so. Say maybe plus the third one, which is Q3 Q over 4 pi epsilon naught R bar R3 bar cubic into R bar minus R3 bar, like so. Say plus, and to the last one we are saying that we have Qn Q all over 4 pi epsilon naught R bar minus Rn bar cubic into R bar minus Rn bar, like so. So in terms of position vectors, this is how we are going to represent our summation of forces. And if we again factor out what is common in that expression, so if we factor out the common terms, we are going to have F bar being the same as what? Q all over 4 pi epsilon naught. That is the only common term. Then you'll sum from K is equals to 1 to infinity over Q K over r bar minus rk bar cubic into r bar minus rk bar, like so. And this gives us our equation number 9. Our equation number 9. And this is how we'll always be expressing our Coulomb's law. It depends on the question that you have in the exam. If the question is dealing with a multiple charges, then you use superposition principle, you get individual forces and you compute that. If the question is only 2-point charges, then you'll use probably those equations that are meant for only 2-point charge. So maybe we can look at some example or an example related to Coulomb's law. Example. So we are saying that a charge Q1 of negative 0.4 microcoulomb is located at point A, which has the following coordinates. And again, coordinate system is very important. If you're not told, the assumption is that it is Cartesian coordinate system. So we are saying that point A, which has coordinates 35, negative 40, and 25 centimeters, while a second charge Q2 of 0.5 microcoulomb is located at point B with that coordinate, then you're told to determine the force on Q1 due to Q2. If you have such a question, it's normally very necessary that you do what? You try to sketch, because these are position vectors. So if we do our sketch here, say let me say that this is my origin at O. This space might be so small again, and we move to this other end. So I have my origin there. I have that and that. Maybe probably there's a charge there. Say call this as Q1. Yep. Then we have another charge here at this point. Call that as Q2. So this is the origin O. So Q1 has the following coordinates. Q1 is our point A, and this is is at point A, and Q2 is at point B, and the coordinates are 35. Then we have negative 40, then 25. This is are all in centimeters. Similarly, we have negative 10, 10, and also 15 centimeters. So assume that this is our vector. Maybe I can call that vector as R1 bar, because it has, R1 for Q1. Similarly, R2 bar for Q2. Now look at our question again. You're told to determine the force on Q1. The statement is very clear. Due to what? Q2. Force on Q1 due to Q2. So how do you go about that? So we can say our force F, it is force on Q1 as a result of Q2. So we are moving in this direction from Q2 upward, that way. And so this is F bar, F bar. So it is 2, 1 is the direction. So we are moving upward. Force on Q1 due to Q2. So F that bar will be F that 2, 1, which is the same as Q1, Q2 all over 4 pi epsilon naught. Let's say this is R 2, 1 bar, and this is R squared A R 2, 1 bar as my vector. Now again, very important to note, when again you have a situation like this, or you are supposed to get force, normally we try first to solve the unit vector. Yeah, and remember what we said about our unit vector. Then we can say here probably that A R21 bar is the same as R21 bar over the magnitude of R21 bar. That is my unit vector being represented as so. So let us try to compute these two terms. So we can say that it is R21 bar can be represented as what? As a vector. Remember the direction is from 2 or B to A, yeah? So from B to A, we are moving against R2, position vector R2, and along R1, yeah? So we can say this is the same as R1 bar minus R2 bar. So now, we have the values here in our coordinates. Actually, these ones represent the positions. So these can be represented as, the first one is that, which represents our R1. So it's the same as 35 minus 40, and then 25 subtracted from negative 10, 10, then 15. So that if we compute that, we have 35 minus 10, that will give me what? 45, comma. Then we have negative 40 minus 10, that will give me what? Negative 50. Then we have 25 minus 15, that translates into 10. Now, if we write this, remember they're still in centimeters, don't forget. Now, this can be represented as 45. Now, as a vector, because it is a vector, it is 45 of AX bar minus 50 of AY bar plus 10 of AZ bar. So that is our vector that's supposed to be substituted here. Then now we are supposed also to get its magnitude. So this is R21 as a magnitude becomes the root of. It becomes the root of 45 squared plus 50 squared plus 10 squared. 5 squared, 50 plus 10 squared. So this translates into 68.01 centimeters. Now at least we have the term here. We have the value. Now we can put in our values in our force now, in our final formula now. Then we can say that F21 bar will be, we've been given Q1, and Q1 was supposed to be negative 0.4, 10 to power negative 6. Remember, it is microcoulomb. Then we are multiplying that by Q2, which is 0.5 times 10 to power negative 6, all over 4 pi. Now, epsilon, remember, we said epsilon was 8.854 times 10 to power negative 12, or we can use 1 over 36 pi times 10 to power negative 9 as being our epsilon. Then we have R, and remember our R is the same as this magnitude. So this value is still the same as our value of R. So we can say that R squared, which will be what? 68.01 times 10 to power negative 2. 10 to power negative 2, I'm changing centimeters to meters. So it is 10 to power negative 2 because this value here of epsilon, which was given here, which is this, is farad per meter. So everything should be in meters, yeah? So that, we have that 10 to power negative 2 Then we square that. Then we have times our unit vector again. Remember, we have our unit vector which is represented as this, and we found that to be 10 to power negative 2 once again, because this value here is in centimeters and we are supposed to change it to meters. And we have 45. I can have 45, comma, minus 50, comma. Then we have 10. Close that. That is over. Another 68.01 times 10 to power negative 2. This is the magnitude that is supposed to replace this. Now, if we try to simplify that, let me just move a bit for space. Now, this will be what? Negative 0.4 times 0.5 multiplied by 10 to power negative 12 all over. Simplify this and this. There is a 10 to power 9 here. I mean, there is 1 over 9. So this will be times 9 times 10 to power 9. This goes up. So we are through with the whole of that term, all over 68.01 times 10 power negative 2 cubic, because this and this term have to be combined. This is square, this is power 1. So we have a cubic there. We still have this multiplied by 10 to power negative 2 into, I can represent that in Cartesian coordinates, 45ax minus 50 ay plus 10 az, like so. Now, if we punch that value with our calculator, if we punch it with our calculator, we are going to get what? This will translate into minus 57.22 into 45 ax minus 50 ay plus 10 az times 10 to power negative 6 newtons. 10 to power negative 6 newtons. So you can open up your bracket and you'll have your final answer as being negative 200,574.9 of AX plus 2861 AY plus 572.2 AZ micronewtons. Remember our unit for force. This is minus, not plus. Negative, and that gives you a negative here. It's a minus. And so that becomes our solution for force. And it's always very important that we also have to indicate our units. Like 10 to power negative 6 is micro, and then N stands for what? Newtons. So that is a very good example, and it's a typical exam question example. Maybe we can look at another example, and then we see what we have to do next. Now, this is our example 2 now. We are saying that the figure below shows 2-point charges, QA and QB, of equal mass and are suspended at a point by 2 threads of negligible mass and length L. Now this is our figure that we have. So we can see our figure there, and then you're told to show that Q squared, which is the same as QA, QB, is the same as 16 pi epsilon naught mg L squared sine squared alpha tan alpha. Then Roman 2 of the equation, you're also told to derive the expression for alpha, assuming that it is very small. Now let us come to our figure and do some analysis a bit on this figure of ours. So if you look at this figure, there is tension caused by the mass on these charges. Yeah? Remember, our charges have some mass, and the masses are also causing a gravitational pull or force, Fg, being given by mass times gravitational pull. At the same time, for these two charges to balance, then there is an electrostatic force pulling them apart. And you're saying that that electrostatic force, Fe, is acting upon QA. Still, we have another Fe acting upon what? QB. Now let us try to prove our expression here. So I'll first wrap this. So now I want to relate this tension that is horizontal to this force. Actually, they are related. The tension is pulling it this way, towards the right, while this force, electrostatic force, is pulling it towards the left. So then we can say that Fe in our solution must be the same as T, the sine of what? Alpha. Similarly again, there is a gravitational pull as a result of Fg that is pulling this downwards, and there is a resistance which is now like our tension again, due to our tension that is moving upward. Yeah? So again we can say from our gravitational pull Fg, we can also generate T cos what? Cosine of alpha. Let me call this as equation 1, and the other one be my equation number what? 2. Now, if I divide equation 1 by equation 2, then I'll have Fe over Fg will be the same as the sine of alpha over T, the cosine of alpha, and this will translate into what? So I'll have Fe all over Fg, and Fg is mg, and that translates into T, and T can cancel. And we have sine over cos, and sine over cos is normally the same as tan of what? Alpha. Still we know that Fe, from our Coulomb's law, because it is an electrostatic force, I can say that, but Fe is the same as QA, QB all over 4 pi epsilon naught. The distance of separation between these two charges is the same as small r, which is r squared. So this is my F. Yeah, this is my equation number what? 4. But that is given by that. So now from that equation 4, we can have this expression here, substitute it up there, and bring mg to the right hand side. We'll have, instead of Fe, it will be QA, QB all over 4 pi epsilon naught r squared. So I'm taking mg to this other side, the right hand side, and that becomes mg, the tan of what? Alpha. Mg tan alpha. Still, instead of having r squared, we can represent this as that r. Yeah? We see I can say maybe but R is equals to twice capital R I can have this as equation number 5 maybe, so that I can say here that but small r is equals to 2 capital R, and if I substitute that again, I'll have QA QB to be the same as, QA QB over 4 pi epsilon naught. So instead of this small r, I'll have 2r squared. That must be mg tan of what? Of alpha, so that we can go further and say that this is the same as QA QB to be the same as mg. Rather, before that, I have 4 pi epsilon naught 4r squared mg tan of what? Alpha. So this 4 multiplied by that 4 gives you what? 16 pi epsilon naught r squared mg, the tan of alpha. That is what we have. See, we are edging closer to what we are supposed to prove. Now look at our drawing. Now if we look at our drawing and we only consider the lengths, because we want to get the value of r, yeah? Maybe I can have a small drawing here that only represent the lengths, because we have a thread and we have that. So that is a section of that. The length from this point to this point is indicated as L, and the length from that to that is indicated as R. Now I want to represent R in terms of L so that I can substitute the value of R there. This angle here is alpha. So if I use my SOHCAHTOA, I can say that the sine of alpha will be the opposite, which is capital R, over the hypotenuse, which is L. This means that R must be equals to L sine alpha. Now if we substitute the value of R in our expression up here, then we can finally get our answer as being Q squared. That is what we had, is the same as QA QB, and that becomes what? 16 pi epsilon naught mg. Instead of r squared, we'll have L sine alpha, L sine alpha tan squared, the tan of what? Alpha, which finally translates into our answer as being Q squared, which is QA QB, and that is 16 pi epsilon naught mg L squared there. Then we have sine squared alpha tan alpha. And that is our solution that we are supposed to get in our Roman 1. Question, you are told to get an expression for for alpha, assuming that the angle alpha is very small. So now, Roman 2, we can say for very small value of alpha, for very small value of alpha, tan alpha will normally approach the value of alpha. Similarly, sine alpha also approaches the value of alpha. So that our solution there, which was q squared, and it's the same as qa, qb, will be 16 pi epsilon naught mg L squared. So instead of sine alpha, you see here sine alpha becomes alpha squared, because we have it as sine alpha squared, and instead of tan alpha, we'll also have what? Alpha, since the value is very small, so it approaches alpha. So this translates into 16 pi epsilon naught mg L squared alpha cubic. That is the same as q squared. So that if we make alpha cubic the subject, (16 pi epsilon naught mg L squared), and so our alpha will be what? The cube root of q squared all over 16 pi epsilon naught mg L squared. And so that is our solution for that particular example.